Hi, welcome back. Today we are gonna take a look at this fueling control panel. This one was installed in a Fokker 100 aircraft. This panel is not located inside the cockpit, but it is located outside the aircraft. There is here a master switch, on off. The fueling can be done automatically or manually. So first you need to set the quantity here, so you can adjust the quantity by this knob. After that, the selector mode here should be set to auto refuel. If the auto refuel is not available or not operational, you can do the fueling manually. Here, in that case, you can use these switches here for the 3 tanks, left, center and right. On the top there are 3 indicators corresponding to the actual fuel quantity in each tank here. On the other side there are 2 connectors. First, let's do a tear down of that thing to see what is inside, and after that I will try to make it work. We can see that the power supply is 28 volts DC. You can see the serial number. This unit was manufactured by Smith Industries. You can see that we have another front panel. Now we have here something serious. There are several electronic boards. Now here there is a board with several resistor arrays. We can see the pass-through capacitors. On that side there is a relay board. We have serious relays here. There are 3 time relays and 3 classic relays. Now this is the power supply board. This board delivers the voltage of plus 5 volts. We can see the marking here. Input voltage is 28 volts DC, which is across this capacitor. This unit doesn't use any microcontroller or microprocessor. It uses standard logic ICs, and it is very complicated to remove the board. Everything is soldered. We can see 2 identical circuits on that board. We have here 2 monostable ICs. This part is a differential line receiver. We have here a board called FPA223. This is a schematic diagram of that board. We have actually 2 current sources. Each current source is connected to 1 pin of the connector, W and G. Obviously, we should have 2 resistors connected externally between these 2 outputs and the ground terminal H. And there is a comparison of the 2 voltages created by the resistors. It uses this op-amp as a comparator, and the output permits to activate an output here, which is connected to 1 pin of the connector, but it is also connected to the relay board. One current source is much higher than the other one. We have one current of 535 microamps. The second one is 27 milliamps. I don't know what is the purpose of that circuit. Probably there is one sensor connected here and a reference resistor here, but I don't know exactly. This current is quite high for a sensor. I did the complete reverse engineering of that unit. It was not of use because it was not possible to remove the board. There is no computing inside, so this is just an interface in order to display something on these 4 indicators here. For that purpose, there are 2 inputs. One input permits to set the values of the left tank here, the center, and the required quantity also. The second input permits to set the right tank quantity. Let's have a look on the schematic. We have here the schematic diagram of one input. The input is here, so this is a differential pair. We can see first that we have here an 8-bit shift register, and we have also 2 D flip-flop here. In total, we have 10 bits. We can see that the output of the receiver here is connected to this monostable. There is on the inverted output here, pin number 4, the negative going pulse. The duration is approximately 40 microseconds, and you can see that the rising edge of this pulse permits to sample the data, which is here. So therefore, this is the self-clocking protocol, and we can see also that we have another monostable here. The duration is 100 microseconds, and we can see that the output permits to reset everything here. This is the timeout of the clock here. So therefore, the duration of 1 bit should be lower than 100 microseconds. We have here the signal for a bit at high level and a bit at low level. We need first a rising edge in order to activate this monostable, and the data is sampled at 40 microseconds here. So therefore, for a high level bit, we need a high level here which is above 40 microseconds, and for a low level bit, the pulse here should be lower than 40 microseconds. So I have defined these values, a duration of 60 microseconds for a high level bit, and a duration of 20 microseconds for a low level bit, and the duration of transmission of 1 bit is 80 microseconds. So this is the main shift register. 1 nibble corresponds to a BCD coding, and we have here 4 lines which permits to select one particular digit. These lines are fed to this multiplexer, which is an HC4514, and we can see that the data is validated when we have a low level at the output of this NAND gate. It is not the stop bit, but this is the start bit, which should be at high level, and the stop bit should be also at high level. The third input here is a short positive pulse. We can see that we have another monostable. The duration is approximately 1.5 seconds. So this permits to clear the display if there is no communication at all. So this is the global timeout for the communication. Of course, the most interesting part is to test this unit. For that, I will use this curiosity board from Microchip. I wrote a code in order to send the data. We have the 2 differential outputs, and I have connected also this switch, which permits to modify the required quantity indicator here. Let's turn on the power supply. It is possible to change separately all indications here. Let's start with the left tank quantity. Center quantity. The right quantity. The required quantity can be changed using this rotary switch here. I have defined a step of 500 kilos. I spent approximately 3 days for this unit. That's all for today. Thank you for watching and see you next time for another video. Bye bye.